Hello again. Today we continue with Computer System Architecture course, Programming the Basic Computer. In the last video, we discussed the first three sections in Chapter 6, Introduction, Machine Language, Assembly Language. And today our topic is the assembler. A program written in any programming language, including assembly language, is called a source program. In order to be executed, this program should be translated into machine language code called object code. If the source program is written in an assembly language, the process of translating it to an object code is called assembling. And the software or program used for this purpose is called assembler. If, however, the source program is written in one of the high-level programming languages, such as C, Fortran, and others, the process of translating it into an object code is called compilation. And the program used for this purpose is called compiler. So assembler can be defined as a software program used to translate a source program written in an assembly language into a machine language program called object code. Today we will use the assembly language program to subtract two numbers described in the previous video. The first number is loaded into accumulator, complemented, and then incremented. So we'll have, after these instructions, the 2's complement of sub in accumulator. After that, this value is added to min, which results min minus sub in the accumulator, and this value is stored in location def. And we will use the tables for computer instruction codes, memory reference instructions with the code 0 or 8 for AND, 1 or 9 for add, etc., 6 or E for increment and skip F0. And the register reference instructions, a clear accumulator with the code 7800, clear E flip-flop with the code 7400, etc., and the halt instruction with the code 7001. And the input, output, and interrupt instructions as well. The code for the input instruction is F800. For the output, F400. And for the turn interrupt off, F040. And all these values are in hexadecimal. For demonstration purposes, we'll perform the translation manually. Here is the source code program. The first line is the org pseudo instruction, org 100, that tells us, or the assembler, to start the binary program from hexadecimal location 100. So we'll have here location 100 in hexadecimal. The second instruction, load, is a memory reference instruction. By checking the memory reference instruction table, here, the code for load is 2 if the addressing mode is direct, or A if the addressing mode is indirect. Since here the addressing mode is direct, then we'll have in hexadecimal here 2. Next, the binary value for the address part must be obtained from the address symbol sub by counting here location 100, 101, 2, 3, 4, 5, 6, 7. So we'll have here 10, 7 in hexadecimal. This is the binary code for the instruction load sub. The next instruction is stored at location 101 in an hexadecimal, and it is complement accumulator. Back to the table. The code for the complement accumulator is 7200 in hexadecimal. So we'll have here 7200. The next instruction is increment accumulator at location 102, and the code for the increment register reference instruction is, here we have it, 70 in hexadecimal. 7020. The next instruction, add min at location 103. Here we have direct addressing mode, and back to the table. The code for add in direct mode is 1. So we'll have here 1. And again, we have to count to find the address of min. Here location 103, 104, 5, 6. So min is stored in location 106. The next instruction, store at location 104, and the code for the store in direct mode is 3 here. So we'll have here 3, and the address of diff, here we have 104, 105, 6, 7, 8, 108. Next, the code for the halt instruction, location 105, and the code for the halt is 7001. Here we'll have 7001. Next, we have 2 lines in the source program that specify decimal operands with the pseudocode decimal here. So in location 106, we have the decimal value 83, and we have to convert this decimal value into hexadecimal. 83 first to binary by 241, and the remainder is 1. 20, the remainder is 1. 10, the remainder is 0. 5, the remainder is 0. 2, the remainder is 1. 1, the remainder is 0, and 0, and the remainder is 1. 83 in decimal equals to 1, 0, 1, 0, 0, 1, 1 in binary. And in hexadecimal, we have here 3, and here we have 5 in hexadecimal. So we'll have here 5, 3 in hexadecimal. And in location 107, the value minus 23 in decimal. Again, in hexadecimal, first 23 in decimal equals to here 1010 0. This is 20 plus 3. 1 0 1 1 1 in binary. And since we have minus 23, then we have to obtain the signed 2's complement representation of this value, which is here 1 0 0 1 0, and all these bits are ones. This is minus 23 assigned to its complement form. And this value is 9. And here we have E, here F, and here F as well. And back to our table. So minus 23 in hexadecimal is F, F, E, 9. Next, at location 108, we have a hexadecimal value 0, all zeros. And the last instruction, end, which is a pseudo instruction, tells us, or the assembler, that we haven't any more lines to translate. So here is the object code or the binary code of the source program used to subtract two numbers. Computers can execute programs if they are in their binary or machine language form. The main disadvantage of this manual translation is that we have to go forward and backward on every time we encounter an address, like here or here or here. If we scan the program and create a table containing these addresses or labels and their addresses, then we can accelerate the process of assembling. And this is the task of the first pass assembler, to create a table called address symbol table. After that, we can perform the second pass by scanning this table and the instruction table containing memory reference instructions and non-memory reference instructions, which are register reference instructions and input, output, and interrupt instructions, as well as pseudo instructions to generate the object code of the program. Regarding the address symbol table, as I mentioned, the translation process can be simplified if we scan the entire Symbolic program twice. No translation is done during the first scan. The purpose of the first scan is to obtain the address symbol table containing the address symbols along with their hexadecimal addresses. The location assignment will define the address value of labels and facilitate the translation process during the second scan. When the first scan is completed, we associate with each label here its location number and form a table that defines the hexadecimal values of each symbolic address. So for our program, this is the address symbol table. We have here three symbols: min, sub, diff, and their hexadecimal addresses: 106, 107, and 108 in hexadecimal. During the second scan or the second pass assembler, we refer to this address symbol table to obtain the address part of memory reference instructions. In memory reference instructions, for example, if we have add X, then this part is obtained from this table, and we do not need to scan the program to find the address field of the instruction. We can retrieve it from the address symbol table. Representation of symbolic program in memory. The symbolic program is stored in memory. The user types the symbolic program on a terminal. A loader program is used to input the characters of the symbolic program into memory. Please note here, although the symbolic program is stored in memory in binary form, it is still a source program. The only difference is that instead of having it on paper, now we have it stored in computer's memory, but in binary form. Each character is represented by an 8-bit code, which is like or similar to extended ASCII code The high order bit is always 0, and the other 7 bits are specified by ASCII. And here we have the hexadecimal character code for the letter A in hexadecimal 41, B 42, etc. The code for the carriage return is produced when the return key is depressed. This causes the carriage to return to its initial position to start typing a new line. The assembler recognizes a carriage return code as the end of a line of code. In basic computer, each location can store at most 2 characters. Since the size of each location is 16 bits, so we can store at most 2 characters, since the ASCII code for each character is 8 bits. A label symbol is terminated with a comma. For example, we have label 1, usually comma, add, increment, etc. A label symbol is terminated with a comma. For example, label 1, comma, and here instruction. Operation and address symbols are terminated with a space, and the end of the line is recognized by the carriage return code. For example, the following line of code is stored in 7 memory locations. Location 1, we have the ASCII code for the letter B, next L for C, 3, 33, comma, 2C, L again for C, D, 44, A, 41. And here we have space, and the code for space is 20. Next, the code for S, U, B, and again space. And the letter I, 49, and the carriage return 00. If the line of code has a command, the assembler recognizes it by the code of a slash 2F. In this case, all characters in the command field are neglected, and the assembler keeps checking for a carriage return code. When this code is encountered, it replaces the space code after the last symbol in the line of code. Again, an assembler is a program that accepts a symbolic language program and produces its binary machine language equivalent. The input symbolic program is called source program, and the resulting binary program is called the object program. The input for the assembler program is the user source program, represented in ASCII code. This input is scanned by the assembler twice to produce the machine language code or the object code. During the first pass, the assembler generates a table called address symbol table, containing all the addresses with their binary equivalent values. And the actual translation or generating the machine language code is performed during the second pass assembler. To keep track of the location of instructions, the assembler uses a memory location called a location counter, LC. The content of LC stores the value of memory location assigned to the instruction presently being processed. The org pseudo instruction initializes the location counter to the value of the first location. If we have, for example, org 200, then the first location is assigned the value 200. After scanning each line of code, the content of location counter is incremented by 1. Here is the flowchart for first pass of assembler. Initially, the location counter is cleared. We scan the next line of code. If we have a label and we have org, for example, org 100, then the location counter is set to this value. location counter now 100. And if it is not org, the location counter remains 0. We scan the next line of code. Suppose that we have entire label, no, and it's not org and it is not end. So we increment the value of the location counter to 101 and we scan the next instruction. And suppose here again we have a label and not org and not end, so the location counter is again incremented. Suppose that here we have a label 1, so here the condition is true, yes, we have a label. So in the symbol address table, we store the value A1 along with its address, 102 in this case. And we increment the location counter and scan the next instruction, etc. Do you see the purpose here is to obtain the symbol address table only? All the labels or symbolic addresses along with their locations. When we encounter end, we start the second pass of assembler. This is the address symbol table for the program of subtracting two numbers. Here we have men and the contents of the location counter. Here is men at location 106. Next sub at location 107 here. And next def at location 108. This address symbol table along with the instruction tables and the pseudo instruction table will be used as source for the second pass assembler. Machine instructions are translated during the second pass by means of table lookup procedures. A table lookup procedure is a search of table entries to determine whether a specific item matches one of the items stored in the table. The assembler uses as input four tables: pseudo instruction table, memory reference instruction table, non-memory reference instruction table, which contains register reference instruction and input, output, and interrupt tables, and the address symbol table generated from the first scan. The entries of pseudo instruction table are the four symbols org, end, decimal, and hexadecimal. Each entry refers the assembler to a subroutine that processes the pseudo instruction when encountered in the program. The memory reference instruction contains 7 symbols, 7 instructions, and their 3-bit operation code equivalent. The non-memory reference instruction table contains the symbols of 18 register reference and input-output instructions, and their 16 binary code equivalent. The address symbol table is generated during the first pass of the assembly process. The assembler searches these tables to find the symbol that it is currently processing in order to determine its binary value. Here is the flowchart for second pass of assembler. First location counter is cleared to 0. The assembler scans next line of code. If it is a pseudo instruction, we check if it is org, then the location counter is set to this value after org. And if it is end, then we are done. If the next line of code is not a pseudo instruction, we check if it is memory reference instruction, then we get the operation code for this instruction from the memory reference instruction table, and we search address symbol table for binary equivalent of symbolic address and set bits 5 to 16. Next, the I bit is checked. if there is an I bit in direct mode, the first bit is set to 1, otherwise in direct mode it is 0. Now we assemble all these parts together, and after that the location counter is incremented, and we again scan the next line of code. If the instruction is not memory reference instruction, here we check it is a valid non-memory reference instruction. If it is not, an error message is reported in that line of code. If it is valid memory reference instruction, we store binary equivalent of instruction obtained from the table for non-memory reference instructions, along with the contents of location counter. After that, we again increment the location counter and we scan the next instruction. If we have a decimal or hexadecimal pseudo-directive, we convert operand to binary in location given by location counter. I did these steps manually at the beginning of the video. One important task of an assembler is to check for possible errors in the symbolic program. This is called error diagnostics. One such error may be invalid machine code symbol, which is detected by not having it in the tables. Another possible error may occur if the program has a symbolic address that did not appear also as a label. In this case, the assembler cannot translate this line of code. In case of errors, the assembler should report and print an error message for each. The assembler explained here is very simple. Most computers have additional assembly language features such as more pseudo instructions, using a number or a symbol to specify an address, specify the address by using expressions, etc. More assembly language features means more complicated assembler. For today, that's all. Thank you.